Okay, in last lecture we have discussed triangular window, and before that we have also discussed the rectangular window. In this lecture we will discuss a series of window which is represented in two parts, hemming and Hanning windows. So we will see that generalized part first, then discuss those windows in this lecture. So we will start with generalized Hamming window. In the previous lectures we have seen rectangular window, problem is sharp transition leading to higher area under the side loops. Remove this particular problem we have used in previous case is triangular window. Which provide better suppression of the ripples, stop and pass band compared to rectangular window. This particular improvement with the triangular window is not up to the mark, so we want to look for another windows which can provide much better results. So for that particular case, cosine function is used. Cosine function comes to rescue and can be used to design a window filter. So one of the case for using cosine for designing a window filter is called Hamming window, and we will start with the generalized form of Hamming window. So generalized form of Hamming window is written as W underscore G N equals to alpha 1 minus alpha cosine 2 pi n over m minus 1 from 0 to m minus 1 and 0 elsewhere. W and generalized is causal as it starts from 0, and the function is valid for both values of m, odd and even. Then if you want to find out the frequency response of W and generalized n is W and G omega equals to summation n equals to minus infinity to infinity W and G and exponential minus of G omega. Now we know this W hand function only exists from n equals to 0 to m minus 1. And over this particular part, the value of this function is alpha 1 minus alpha cos 2 pi n by m minus 1 exponential minus of j. Then we can write this equation as n equals to 0 to m minus 1 alpha exponential minus j omega n minus 1 minus alpha summation n equals to 0 m minus 1 cosine 2 pi n m minus 1 exponential minus j omega n. Then it is equal to alpha summation n equals to 0 m minus 1 exponential minus j omega n minus 1 minus alpha summation n equals to 0 m minus 1. This cosine can be written in the form of Euler's identity, and then it will be equal to 1 minus alpha by 2 exponential j 2 pi n by m minus 1 plus exponential minus j 2 pi n by m minus 1 into exponential minus of j omega n. Let for the clear representation we can write 2 pi by m minus 1 equals to beta. Then equation can be written as alpha summation n equals to 0 to m minus 1 exponential minus of j omega n minus 1 minus alpha by 2 summation n equals to 0 m minus 1 exponential j beta n into exponential minus j omega n. We'll make a bracket here, and then there is a plus sign plus summation n equals to 0 m minus 1 exponential minus j beta n exponential minus j omega. We can see this particular part that exponential minus j omega n is nothing but a geometric progression. So we can write this term as alpha 1 minus exponential minus j omega m over 1 minus exponential minus j omega. That is the sum of finite geometrical series. So then similarly we can do for this part, that is 1 minus alpha by 2 1 minus exponential minus of j omega minus beta m over 1 minus exponential minus j omega minus plus 1 minus exponential minus j omega plus beta into m over 1 minus exponential minus j omega plus beta. Then taking exponential minus j omega by 2 common in each cases, then alpha exponential minus j omega m by 2 over exponential minus j omega by 2 sine omega m by 2 over sine omega by 2, then minus of 1 minus alpha by 2 exponential minus j omega minus beta m by 2 over exponential minus j omega minus beta by then sine omega minus beta m by 2 over sine omega minus beta by 2. then plus exponential minus of j omega plus beta m by 2 over exponential minus j omega plus beta by 2. It will be sine omega plus beta m by 2 over sine omega plus beta by 2. So we have written this particular equation with all the phases and with all the values in it. We can write it like this: alpha exponential minus of j omega m minus 1 by, and then it is sine omega m by 2 over sine omega by minus, or we can make this particular term right now minus, then we'll adjust this particular negative sign, 1 minus alpha by 2, and then it will be exponential minus j omega minus beta m minus 1 by 2, and then it is sine omega minus beta m by 2 over sine omega minus beta by. Similarly, we can write plus exponential minus j omega plus beta m minus 1 by 2. Then again we can write sine omega plus beta m by 2 over sine omega plus beta by 2. We have the window function, and we already knew we are much more interested in the magnitude part instead of the phase part. Alpha exponential minus j omega m minus 1 by 2 sine omega m by 2 over sine omega by 2. This minus sign will be adjusted with the phase, so we can make 1 minus alpha by 2 exponential minus of j omega minus beta m minus 1 by 2 plus pi, and then sine omega minus beta m by 2 over sine omega minus beta by. Similarly, the response we have obtained, and if we want to find out only the magnitude response, w m omega is equal to alpha sine omega m by 2 over sine omega by 2 plus 1 minus alpha by 2 sine omega minus beta m by 2 over sine omega minus beta by 2 plus 1 plus alpha by 2 sine omega plus beta m by 2 over sine omega plus beta by 2. Please note that we have substituted the value of beta, that is beta is equal to 2 pi by m minus 1. So that is an important part we have to keep in mind. Now value of alpha will decide the impact of the window. If alpha is substituted as 0.5 or equals to 1 by 2, then the window is called Han or Hanning window under the name of the physicist called von Hahn. This window is also known as raised cosine window. Then the points we can see, first is main lobe width. The main lobe width in case of Hanning window is 8 pi by m, which is equivalent to triangular window, but twice to rectangular window. For rectangular window, the main lobe width is 4 pi by m. Next is peak side lobe to main lobe ratio. In case of Hanning window, the ratio is minus 31 dB, which is smaller than rectangular window. Which is minus of 13 dB and also smaller than triangular window. That is minus 26 dB. Third point is attenuation in stop band. Attenuation in stop band for Hanning window is 44 dB, which is larger than triangular and rectangular window. That's mean using Hanning window will give a main lobe width equivalent to triangular window, but peak side lobe to main lobe ratio and attenuation in stop band better compared to rectangular window. Then we'll quickly move towards another window which is called Hanning window. For this particular case, alpha is equal to 0.54 and then the main lobe width in this case is also 8 pi by m, which is equivalent to Hanning window and triangular window but larger than the rectangular window, which is 4 pi by m. Next is peak side lobe to main lobe ratio, which is in this particular case is minus of 42 dB, which is smaller than the Hanning triangular and rectangular window. So by varying the value of alpha, we have improved this particular property. Next is attenuation in the stop band is in case of Hanning window is 54.5 dB and which is larger to Hanning triangular and rectangular window. One can see by varying the value of alpha, we have improved over the Hanning window also, and this particular window is called Hanning window. We'll quickly compare these particular windows. So the comparative table can be seen like this. So window for rectangular window, the main lobe width is 4 pi by m. Main lobe width will also define the transition band. band from pass band to stop band, right? So main lobe width is minimum for rectangular, that is 4 pi by m. For triangular, Hanning and Hamming, it is 8 pi by m. If we see peak side lobe to main lobe ratio, the Hamming window has the highest separation, that is of minus 42 dB. Then we want attenuation at the stop band to be very high. Rectangular window has only 21 dB, whereas in terms of Hamming window, it is 54.5 dB, which is very large compared to rectangular window. Also one can see, so if alpha varies, one can move towards Hanning, and there is a drastic changes in the properties of the filter. First, we'll see the windows in time domain. So first window is rectangular, right? And then another window is triangular window. Then we have, one can see the samples are varying like a triangular fashion. Then we have a Hanning window. This is also called raised cosine window. One can see the pattern of a cosine wave. It's 0 at the edges and maximum at the center. One can say it is pi by 2. After Hanning window, we have discussed Hamming window. One can see at the edges, like at minus 20 and 20, cosine is not going to 0 but have very small value, right? So it is also called raised cosine with flat form. Then after time domain representation, we can see the normalized frequency response. There are a lot of side lobes which contains lot of area in rectangular window due to this sharp transition at minus 20 and 20. When we move towards the triangular window, these side lobes are somewhat reduced compared to rectangular window. When we move towards the Hanning window, it has only one dip at this particular point and then it is nearly constant. It's nearly constant, and when we move towards the Hamming window, that particular dip is also gone and the side lobes are nearly vanished. So that's mean peak side lobe to main side lobe ratio is very low in Hamming window compared to Hanning window and triangular window and rectangular window. It can be seen from this normalized frequency response. One can also see that the main lobe width of rectangular window is smaller compared to triangular, Hanning window and Hamming window. That is the trade-off we are facing. Then we can see the normalized frequency response in decibels. So one can see it is 0, that is the gain at pass band, and minus 13 dB, it is the ratio peak of side lobe over main lobe. Similarly, for triangular window, it is minus 26 dB, and then it is further reduced in Hanning window to minus 31 dB, whereas in Hamming window it is reduced to minus 42 dB. But one can clearly see the transition is much sharp in rectangular window compared to triangular, Hanning and Hamming window. So these response should be kept in mind for designing an filter. Depending upon our application, we will choose which window is optimal for that particular operation. That's all for today. We'll discuss Blackman window in next lecture. Thank you.